Okay, in this video we're going to be looking at solutions to the review problems that I presented in the last video. We'll do a number of them in this one. We may break it up into a few videos here. So the first one is we're given a graph of a relation like this. This is one single relation. It's broken. It's got different formulas for each piece, but we don't care about the formulas right now. And I'm going to ask you several questions about that. Is it a graph of the function, and how do we know? Well, yes, it is. And the way we know is because it passes a vertical line test. If you draw any vertical line, say such as the grid lines here, it either touches the graph in one place or in some cases doesn't touch the graph at all. But it never touches in more than one place. So it is the graph of a function. What's the domain? Well, it's all real numbers except for just a few places. Notice here when x is -2, there's no y value. There's no point on that vertical line. Same goes for when x is 0, when x is 2, 14, and 15. -2, 0, 2, 14, and 15. So it's all real numbers except for take away those values. The range is actually all real numbers. For example, this piece here alone picks up all possible y values, and then some of the others, some of the y values, in fact all of them are repeated at least more than once. The limit as x approaches 12 is 0. Let's see if we can see that. As x approaches 12, the f of 12 is 0 and the limit is 0. So in fact the function is continuous there. Those two. The limit as x goes to 0 of f of x is 2. So let's see what happens at 0. As x comes into 0, gets close to 0 here, y gets close to 2. So that limit is 2, but the function does not exist there. So f of 2 does not exist. F of 0 does not exist. F of 0, f of x approaches 2 as x approaches 0. So 0, 2 is a hole in the graph or removable discontinuity. What's next? We're going to see what happens at 10. Okay, at 10, the limit from the left is, looks like about 12.5. The limit from the right goes to negative infinity, which doesn't exist, but it's better to say negative infinity there because it's more descriptive. And f of 10 is actually 8. So we have an isolated point here, an open dot endpoint there, and a vertical asymptote here. I think that is reflected by the notations here. There are other ones that we could ask about this same graph if we wanted to. It'd be interesting to talk about some other places. Okay, some formal definitions. For given a function f and a real number constant c and l, we say the limit as x approaches c of f of x equals l if and only if for any epsilon greater than 0, there exists a delta greater than 0, such that if c minus delta is less than x, which is less than c plus delta, but x is not c, then L minus epsilon is less than f of x, which is less than L plus epsilon. So if x is close to c within delta of it, then the f of x, the output, has to be close to the limit value L. How far? Well, within epsilon. And no matter how small we make epsilon, we can pick a delta to go with it that's small enough so that this will happen. We'll come back to that idea in a question a little bit later on. A function is continuous at x equals a if and only if the limit as x approaches a of f of x equals f of a. Notice that that's three things. The function must exist, f of a must exist. The limit must exist, second thing. And the third thing, those two things are the same thing. Question 3. Consider this rational function, 2x squared minus 7x minus 15 all over x squared plus 4x minus 5. First thing you want to do with this is factor it. So using anti-FOIL factoring, we can factor that out as 2x minus 3 times x plus 5 in the numerator and x plus 5 times x minus 1 in the denominator. If you remember how that works, you see how to get 2x squared. The only choice is 2x and x. To get x squared, it has to be x and x. For 15, we could use 1 and 15 a 3 and 5. One's positive, one's negative. The one that works out is -3 and +5. We get -3x plus 10x is 7x for the middle. And so you set up to make sure you get the F and the L to work, and then you keep working at it to get the O and the I to work out correctly. So 5, it has to be 5 and 1, one positive and one negative, and the only one that could works is the +5 and -1 here. And you can double check that with FOIL. Now notice these both have a common factor of x plus 5, so the fundamental property of fractions says as long as that x plus 5 is not 0, we can cancel that out, and it's the same as 2x minus 3 over x minus 1. But we do need to put this restriction that x is not -5, because if x is -5, this thing does exist, but the original over here does not exist. So x equals -5 is not in the domain, and neither is x equals 1. X equals -5, you can plug in and get a value here, and we'll see that that is the value of this limit right here, which you can work out this way, which I have right down here. After the reduced version, you can actually plug in -5 and work this out. That's -10 plus -3 is -13, and this is -6. That's 13/6, or 2.1 with the 6 repeating. And oops, I don't have the table finished here, but you can work out the values there, and what we should be seeing is they get closer and closer to 2.16 repeating. Let me pause this for a second. I'll fill those in. Okay, so here I put in the formula here in a TI-84 calculator. I went to the table, set it up to on an ask table so I can put in what I want for the values here. And I've already picked out some good values. So I can put in some of these, -5.1, and that gives me, let's see here. Let me just go ahead and do a few of these, -5.01. Notice these are x's are getting closer to 5, but they're staying below. It's closer to -5, but they're staying below -5. Okay, and by putting the cursor on the value here, I can see even more digits. Okay, so let me type some of those in here. 2.1639, 2.1664, 2.1666, and then 4, and the next one. Oops, I got the same one in there twice. Let's change that a little bit. Um, 2.1, looks like there's 4 6s and a 4. I bet this is 2, given the pattern. 1, 5 6s and a 4. Let me check that out on the calculator here. -5 point, and I want 4 zeros. A 1. And if I go over here, yep, works out the same way. Okay, so I'm going to go over here now. I'm going to go ahead and just delete those out, and I'm going to put in some of these others. Working from the right side of the table, -4.9, -4.99, -4.999, and -4.49s. And if I write those down, this one was 2.1695. This one was 2.1669. This one is, okay, so we got a nice little pattern going here now. 2.136s and a 9. This is a 2.146s and a 9, and so forth. So the idea here is we notice that as we're getting in closer to -5 in the middle, where the function is actually undefined, if you actually put in -5 in the original formula, you would actually get an error message, or undefined. And but these y values are getting closer to 2.16 with the 6 repeating. And we see that that's exactly what we get here when we plug in -5 in the reduced version. So what does that tell us? That tells us that -5, 13/6, or -5, 2.16 with the 6 repeating, is a hole in the graph, a removable discontinuity. Compare and contrast that when what happens when x is 1. This time we see that as we put values here that are close to 1 but below 1, and we get coming from this side, the values keep getting bigger and bigger, positive numbers. But when we put in values bigger than 1, we get negative values for the output. And as they get closer and closer coming in here, they get, well, smaller and smaller, bigger and bigger in absolute value, but going down. So we would say that the limit as x goes to 1 from the left side is infinity, and the limit as x goes to 1 from the right side is negative infinity. The full limit does not exist. In fact, the one-sided limits don't exist, but this is more descriptive. So in fact, this is going to say that we have a vertical asymptote. We also know that if we reduce the fraction and we put in x is 1 here, we get a form of a constant over 0. So we know that that's going to approach positive or negative infinity from each side. And a little bit of investigation shows you that it has to be negative infinity from the right side and positive infinity from the left. And so that tells us that we're going to have a vertical asymptote. Okay, and it is going to be from both sides there. And that vertical asymptote, of course, is the line x equals 1. And when you look at a graph, okay, well, we'll get to a graph in just a minute. Let's go ahead and do the left and right in behavior. So here I've worked this out. Again, I use my calculator to do this. So if we start, say, at 100, we get about 1.99, let's say, and then 1,000, 1.999, 100,000, 1.9999, a million, 1.999, 1.69 there. And so we see that these are always a little bit less than 2, but they're getting closer and closer to 2 as we go out to the right. That indicates a horizontal asymptote of y equals 2 on the right side. So that says that the limit as x goes to infinity of this function is just 2. As we go to negative infinity, it also approaches 2. In negative 10, we get 2.09. Negative 100, 2.0099. Or if we want to say negative, we could say 2.1, 2.01, 2.001, 2.3 zeros and a 1. This is 2.5 zeros and a 1. And so we see that these are always a little bit larger than 2, but getting closer and closer to 2. So the graph is above y equals 2, but coming down closer and closer to it as we go to the left. Again, that limit is 2, and so that indicates a horizontal asymptote. We know that whether we're using this version or the reduced version, one way we can do is they're going to have the same limits as we go to infinity or minus infinity, and a rational function is going to be the same on both ends. One way we can see this is to multiply top and bottom of this fraction by 1 over x, in this case, to get that to be a constant and that a constant term. As x goes to infinity, these parts go to 0, and we're just left with the 2 over 1. We could have seen that from the beginning by just taking the ratio of the first terms here, 2x squared over x squared is 2, and since that's a constant, that's the constant that is approaching. So y equals 2 is our horizontal asymptote, which you see here on the far left and the far right. Our vertical asymptote was x equals 1, which you see here. And our hole in the graph is here at -5, comma, what was it? 13/6, 2.16 something. Okay? And so that gives you an idea of what the graph looks like. So notice this one, the domain is all reals except for -5 and 1. And the range is all reals except for 2 and also whatever that was, 13/6, I believe. Okay, let's go ahead and stop this video here, and we'll come back and look at some more solutions in the next video.